All right. So 11:35. So our last lecture before the break. Next week is the midterm, and I'm just thinking. I'll confirm that I believe that's just going to be half a class, right? So the midterm is 80 minutes, and I maybe will just leave it at that, and maybe I'll have a lecture after. I have to kind of evaluate where we're at in terms of the material. Probably just half a class next week, though. Of course, your assignment 2 is due this week as well, so a lot of preparation if you're if you're still working on that. Yeah, we'll have my office hours on Thursday, 10 o'clock. Or you can drop in for 5 minutes, basically any time, or you can make an appointment sometime outside of those times if you want some help. Yeah, so today we're going to finish talking about skip lists, and then we will look at so there is a practice midterm that is up on Brightspace. We're going to take a look at that, just sort of do a quick run through of how you would approach these questions. So the actual midterm is going to look a lot like the practice midterm, right? Just some different numbers and things, but the concepts will all be the same, right? So nobody's trying to surprise you on the midterm. So you know what you have to study, and we'll go through that. But first, we'll finish talking about skip lists, because skip lists do appear on the midterm. Hash tables, which come next, don't appear on the midterm. Okay, so skip lists is the cutoff. But yeah, any questions before we get started? Okay. Not on the midterm. The final, yes. But the midterm is just, you'll see. I mean, the questions, they're not hard, though. They're short answer. A little bit of programming. You'll see after the after skip list. Okay, so we did start talking about skip lists last week. We'll quickly review what we talked about and then get a little bit deeper. Yes, I am going to go over the practice midterm. I'll answer any questions you have. I mean, it's not that difficult, or rather, it's very straightforward, right? You have to study, though. But skip lists do appear on the midterm, so I'm going to wait till we're done the skip list lecture before I go over it. That's all. Okay, so skip lists are loosely based on, well, the problem that they solve is basically we have poor performance on a lot of list type structures, right? And by poor, I mean, if I, for instance, add somewhere in the middle, let's say I have 1,000 items and I call add 500x, then almost no matter what I'm using, this is going to be bad, right? And by bad, I mean I'm going to have to do 500 operations. So if it's a linked list, I'll have to start at either the front or the back. It doesn't really matter. If I'm adding to the middle, I'll have to walk through 500 items, and then I can insert really quickly. If it's an array stack, for instance, I have to, well, I can get there really quickly, but in order to make room for this X data element, I have to move a bunch of stuff out of the way. So I have to move 500 things. And even array decks are very good at adding and removing from either side. But the middle, of course, it's still kind of slow. But on a skip list, we can add in the middle kind of quickly, like log of n, right? So log base 2 of 1,000 is something like, what is it, 8 or I don't know, somewhere around there. Maybe more than that, maybe 10 or 12. Anyway, so that's way less than 500. So that's the idea behind these skip lists. And they make use of randomization, but in some sense, they're a lot like, if you guys are familiar with balanced binary trees, they behave very similar to that. So we're gonna sort of take a look at what I mean by that. But so we start out with to make a skip list, we start out with a linked list, a regular singly linked list. And then, well, some of these nodes are going to be promoted into other linked lists, right? So instead of just a single next pointer for any given node, say this guy, I have 4 of them, which means that this node appears in linked list 3, linked list 2, linked list 1, and linked list 0, and every piece of data appears in linked list 0. But the idea is that, well, every time I go up a list, about half of the nodes are promoted. So that means that if I start looking for something, I can start at the top, and I can skip a whole bunch of items. And in fact, on average, I can skip about half, right? We'll get into that a little bit, sort of what I mean when I say we can always skip about half. Yeah, so, and this is really so that drawing that we have there is just it's a nice visual representation for us. In terms of what's actually happening in our code, it looks closer to something like this, but this is of course ugly and harder to evaluate, whereas this is nice and pretty. So yeah, we get fast speed up by skipping elements. That also gives us a fast add and a fast remove. Our node is a little different now. Not too different though. We have a data element X, and we have a next pointer, but now we have an array of next pointers. And the size of this is going to be the height of our node, right? So when we make a new node, we basically flip a coin a bunch of times to see how high it's going to be. I forget exactly everything we went over, so I'll just go over it all very quickly. Yeah, so let's see. I think somebody is. Oh, lots of people are unmuted. Okay. So when I make a new node and I want to add it, so it's going to add similar to when I have a singly linked list, right? So I'm going to insert it in a bunch of different linked lists, but of course there's a nice, it's not quite as simple as that sounds, but initially when I want to add a data item, I'm going to create a new node for it, and I'm going to randomly decide how high it is by flipping a fair coin, right? And basically, I start out with a node X, and I'm always in list number 0. And then I flip a coin, and if it comes up, what do we say? If it comes up heads, we promote it. And if it comes up tails, then I'm done, right? As soon as it comes up tails, I'm done. So if I flip once and I get heads, I go into the next list, and maybe I flip my coin again and I get heads. Well, then I go into list number 2 in this case. And let's say I flip my coin again and I get tails. Well, then I'm done. Right. So as soon as I get tails, that's as high as I go. And, if it's a fair coin, we're going to sort of go over the math again. You don't really have to. I'd rather you get the intuition correctly. I'm not going to test you on. I don't want to say I'm not going to test you on math, because some math is just implicit. You have to know it for this stuff. But things like expected value, things like that, I'm not going to test you on directly. Yeah. Okay, yeah. I'm trying to be consistent with the midterm now, but I think I got, yes. So I read the instructions carefully, all right? Because yeah, heads, tails, it's the same thing, right? Both have basically I promote it with a probability of 1/2, and I stop promoting it with a probability of 1/2, whether I label those heads or tails. But yeah, you are correct. I am saying actually this at this point, not what's written there. But again, that's sort of, if I mix those up, you should still understand that, the process. Yeah, any other questions? Okay. So that's it. And then once I do that, I can insert it. We'll look at the details of exactly how. But since this is we're going to talk a little bit about the randomness. We're going to talk about what happens on average. But one of the sort of important things is how high do we expect these nodes to be, right? So how high are they on average? So here I sort of have a drawing that, these are sort of maybe a little bit unreasonably high. And also we want to determine the height of the skip list on average. So every time I promote, if I insert a node here, I have my sentinel, which is the head of my skip list, and it's always as high as the highest node, right? Because, well, if not, then I have no way to skip to this node in list number 5. So it has to be as high as the highest node in order to include, otherwise it's pointless to have, right, if this guy wasn't here, it would be pointless to have this node as high as it is because there's nothing in list number 5 now, or at least I can't access it. So yeah, the sentinel is as high as the highest node. And so yeah, what is the expected height of a node? Which we will, actually, does anybody know off the top of their head? So it's the question is, I flip a coin, it's a fair coin. How many times do I flip it until I see tails? And yes, the answer is 2, right? Or heads, right? Either one, we're talking about averages. So it's possible I flip it and I see a lot of tails before I see heads, for instance, or I see a lot of heads before I see tails. But if I average out everything, it's going to average to 2. I flip it once, I see tails. I flip it once, I see heads. That's the average. So that means the expected height of our node there is going to be 2. And we'll talk about the implications of that. All right. So yeah, the sentinel, as mentioned, is the head of the skip list. And then the key feature is that the search paths are short, right? So we are going to show that the average search path is 2 log n plus some constant, which is big O of log n. And we did talk about how much shorter that is than, on a million nodes, big O of log base 2 of a million is about 20. So it's fast. Very quickly, the search path. Well, if we call find 4, we actually find the predecessor of 4, right? And it's a design decision that Pat made. So we're going to abide by it. That we can find items directly in our algorithm. Find 4 finds the predecessor. The reason being, if I want to add something, I want to look for that thing, but I want the path to the thing before it so that I can add it to all of those linked lists, right? So if I call a find function in my add, I need to find the predecessor in order to properly be able to put something new in my list. But find 4 means find predecessor of 4, which means that, well, I start here and I look, I can see this item. This is sentinel.next at height of 5. And I see this node and I say, well, is this node, or is the thing I'm looking for less than this? Is the thing I'm looking for less than or equal to this? And if so, I'm not going to proceed to that. If it's less than, I go right. Yeah, I'm blanking on the less than or equal to stuff. Regardless. So I look at 4. The thing I'm looking for is if it's 4 or less, then I'm just going to go down. Okay, so I start here. I look, I see that the thing I'm looking for, or the thing I'm looking at, is not, whatever. For whatever reason, I'm terrible at less than or equal to and +1, -1. So yeah, you guys got to figure it out. I look, I see 4, that's too high, I'm going to go down. I look again, I see 4, that's too high, I'm going to go down. I see 2, 2 is less than the thing I'm looking for, so I can go to the right. From here, I look again to the right and I see 4, 4 is not less than the thing I'm looking for, so I go down. 3 is less than the thing I'm looking for, so I go right. 4 is not less, so I go down, and then I go down again, and that's my search path. Right, so find predecessor. This would also be a valid search path if I'm searching directly for 3. Yeah, that's why I test everything, because I don't know, man. I will, if there's a mistake anywhere in my code, it's going to be there, at least there, maybe some other places. So yeah, I found the predecessor to 4. If I wanted to find 4 directly, I mean, I could also do that, right? There's nothing stopping me from writing code to do that. I look to the right, I see, yes, this is the thing I'm looking for. And then I could travel down. Technically, I don't need to take all of those steps. Once I found 4, I found 4, but for the sake of the midterm, I would have you consider approaching this algorithmically and just, if I'm searching for 4 directly and I find myself at the node containing 4, then I want you to also count every step down. We'll talk about that when we talk about the midterm. But yeah, that's the search path for finding 4. I just find the predecessor. This gives me some certain advantages that we'll talk about. Okay. So we're going to implement the sorted set interface for this skip list. So sorted set is I implement add X, remove X, and find X. And all of those rely on find X, right? So every time if I want to add or remove something, I have to either find it or I have to find the predecessor to it so that I can add it. So add, remove, and find all rely on that find operation that we just talked about. And in this implementation, when we say find, we mean find the predecessor node, right? That just gives us more options than the regular find. Okay, question so far? All right. So our skip list looks something like this. We make a sentinel node. We have a variable h that keeps track of the current height of the skip list, right? Well, we'll see why exactly, but we have a variable n that keeps track of the number of elements stored in our skip list. We also have a stack. It's in the notes. I sort of regret putting it there. However, for a sorted set interface, we use the stack as sort of a memory of the search path, right? So as we go, we'll talk about it later, but when we implement the add function, we don't add right away because, well, we'll see when we get there. The stack is basically a memory of the search path, and I'll show you how we use it when we get there. Okay, so find predecessor node. I start at the sentinel and I start at the top, right? So R is the current height. So while I'm still not in list 0, I keep looking for the thing, right? So this u.next at R not equal to null. So let's say I'm here. Technically, these are not shown, but these should all be set to null, right? So same as with a regular linked list. At the end of my linked list, I want to have some sort of stopping condition. So what I do is I just set the pointer to null. And that indicates that that's the end of list, in this case, number 5. And here, this is the end of list number 4. This is the end of list number 3. So at some height, I keep walking to the right as long as the thing I'm looking for is less than the thing I see. Wait, yes. As long as the thing I'm looking for is less than the thing I see, I keep walking to the right. Right, so this is my step to the right. These are the blue arrows, as mentioned here. R minus minus is the green arrows. So this is every time I decrease in height. Right, so this is just the sort of pseudo-Java code of the process that we talked about, that find path. Questions? Okay. Yeah, so does this work? What if X is the first element? What if the list is empty? These are worth considering when I write a piece of code. If X is the first element, what happens, right? So what if the thing I'm searching for is here? Well, this find predecessor node is still going to return a node, right? It's going to return the sentinel, which that's okay. That's a node, and I have direct, fast access to that first element. What if the list is empty? What if the list is empty? So that means that I have a sentinel. Well, actually, if the list is empty, the sentinel, the height is 0. And this points to null, right? So the sentinel is always as high as the highest node. If I have no nodes, then the height is 0. So, well, r is greater than or equal to 0, that's fine. While the current node dot next is not equal to null, well, I'm going to bump out of that while loop right away. I will decrement r. I will bump out of this while loop. I'll just return the sentinel, which again, that's the one I want to return. So it's always good to think about these edge cases when you, I'm sure if you started assignment 2, you realize the edge cases are the bane of your existence when you're writing these types of data structures. A lot can go wrong there. So yeah, it's always worth sort of looking at what happens. Okay, so if I have a find predecessor node, then find is easy, right? I call find predecessor node, it returns some node. If the thing that I find is null, I return null, right? If maybe my list is completely empty and the next thing I look at is null, then I return that. Or if I yeah. It's possible I don't find it, right? So this, we talked a little bit at the beginning of the year, but it was a long time ago. So let's reiterate what find does in a sorted set versus an unsorted set. So if I have an unsorted set, find might return null if, well, if I can't find it, right? So I either find exactly what I'm looking for in an unsorted set, in which case I return it, or I don't find it and I return null. Okay, but for a sorted set, it's slightly different. I return the least thing that, or sorry, the greatest thing that is still less than the thing I'm looking for. So when I call find on a sorted set, it's possible that X is not in this list, but I still return what would have been before it. Okay, so perhaps that's null. If the thing I'm looking for in this list, let's say I looked for 6, or even 10, right? So 10 is, of course, it would be past 5, but 10's not in this list. So it's going to return the predecessor. It's going to return 5. And then when I check to see, well, is the next thing null? Yeah. So that means 10 is not in the list, but also 10 is greater than everything else in the list. So I return null in this case. Otherwise, I return the thing that comes just after X. All right, does that make sense? Questions? So that's just, the reason for that is because this type of operation might be used for something like I want a sublist, right? So I have a list of sorted items. I want everything that comes after J in the alphabet, right? It's a bunch of strings. I ask my skip list to return everything that you contain that is J, starts with J or some letter after J. Well, maybe there's no letters in the skip list that start with J, but I still want everything that comes after it, right? So that's why find, in this case, will return something. It will split the list effectively around the value that I'm looking for. All right. Okay, so this is I put it here like this because this is what it is in the actual code, right? So assignment 3, you'll be working with a skip list, and the pick height does this. This is essentially flipping a coin 32 times, but it's slightly faster than actually calling rand next Boolean over and over again, which is what we would do. So every time right? Rand dot next Boolean, while it is true, I say I increment the height. But this is, I guess, a little bit faster if you get down to the bit level. So what it does is it picks a random integer. The random integer has a binary representation, right? So it has it's some sequence of ones and zeros. And then what we do is we look at, well, how many trailing ones are there? And that's essentially, since this is a random int, every bit is also random. So this is like I flipped heads, 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 tails. Or rather, the probabilities are the same, right? So this is just a fancy way using bit manipulation to do a slightly more efficient pick height. I don't think it would really matter if we use the simpler way to do it, but this is what's in the textbook. This is what's in the ODS library. So just to explain what it's doing, it does essentially the same thing as flipping a coin. Okay, questions? All right. Okay, let's talk about add. So I want to add to my skip list. Let's say I want to add the value 2.5. Well, I've left a little bit of space here. We know that it's supposed to go between 2 and 3. Again, it's going to use the find operation. But let's again talk a little bit about the sorted set interface and the add function. So on a sorted set, I do not contain duplicates, right? It's a set. So when I add X, if X already exists, I do nothing. So when I add 2.5, well, first of all, let's talk about the simple case of, let's pretend 2.5 not in there, and let's say I know that it's not in there. Then I can simply add it by searching for it, right? So again, I'm going to call a find predecessor of 2.5. And I know what the find predecessor is going to do. It's going to take this search path here and then down to the base. So that's my search path. So now I want to add 2.5. I'm going to make a new node. That node is going to contain the data, and it's going to have some height. So let's say, for instance, that it has a height of 3. Okay, so as I go down the search path, I look to the right. I see that 3 is greater than 2.5, so I'm going to go down, but if 2.5 was higher, right? So before I go down, I want to check to see, well, should 2.5 go into this list? Should it go into list number 5? And if so, I'm going to change these pointers, right? The same way I would in a singly linked list, nothing too difficult. In fact, you guys are supposed to do it for assignment 2. So yeah, if my node is not that high, I just go down. I don't have to worry about it. I don't have to change a thing. I just keep this pointer pointing to the node containing 3. Okay. So then I go down here, down here. I look to the right. Yes, I'm going to go down, but in this case, I know 2.5 should go in here in this list number 3. So I'm going to, change these pointers. So if this is node U, I would say U.next at the current height equals, if this is W, I would want this set to W. But before I did that, I would want to say W.next at the current height equals U.next at the current height. Right. So step 1, step 2. Step one is I point this guy at the same thing that this node is pointing to, and then step two is this is really looking like a mess right now. There is a neater version of this coming up. But I stitch it into the list. The only difference is now I have to indicate which list I'm stitching it into. Okay, but otherwise it's the same operation you've seen in a singly linked list. Okay. Sorry, just a loose wire, I think. All right. Okay, so add, we want to find the correct place and then move some pointers. So that's what would happen if I knew that 2.5 wasn't in there. Along my search path, as I go, I simply stitch that node into the list if the node is high enough. However, because I'm implementing the sorted set interface, I have to take the extra step of actually looking for, right? So maybe 2.5 exists, but only in list number 0. So if I make a new node and I start adding this, right? If I make a new node, 2.5, and I start adding it in to every list, then I'm going to find, oh, I've just added something that already exists. Okay, so first we have to search on an add, and then we are going to go back and stitch it into all those lists. So that's why we have the stack. So my search path is still defined predecessor search path. But instead of inserting it at this point, we're going to save it to a stack, right? The stack was simply an array of nodes. And then I say, well, stack at 5 is equal to the sentinel. Stack at 4 is equal to the sentinel. Stack at 3 is equal to this node here. Stack at 2, 1, and 0 is equal to this node, right? So this keeps track of our search path. It's just an array of nodes, basically, that we call a stack. And then we can use that to add in the node if we find that we get down to here and we see that, oh, 2.5 doesn't exist, so actually I do want to make a new node and added it. I sort of regret overcomplicating this with this part, but that's essentially what happens in the Skiplist set class. Okay, so now I've gone to I found the search path, I've stored it. I make a new node for my 2.5 because I didn't find it. And then I go back and I stitch it in just by going down the stack. Questions? All right. So my add function, so this is my find predecessor node. And the add function, I put it here because we're going to see just how similar it is, right? So essentially, I do the same thing, except now I need to keep track of this comparison because if I have to check to see if I've actually found the thing I'm looking for, right? So this add is essentially a find predecessor with a couple of extra steps. One, I store this comparison so that later I can check, oh, maybe I'm here and I look to the right and I actually do see 2.5, in which case I just return false. I say, well, this thing is already in the set, so I'm not going to add it. Otherwise, I decrement the height, but I also store whatever my current node is on my stack. And Yeah. So if I get to the bottom and I have not found 2.5, I still have a record on my stack, and I use that in order to stitch it in, right? So as we talked about, w.next, w being the node that I made for x. So this would be w is equal to stack.next, right? So my stack is pointing over here. And so I set this guy to point to the same thing. And then I set this to point to this node, right? So it looks kind of complicated, but the actual thing that you're doing is the same thing you would do in a singly linked list. Afterwards, increment n, return true. I did actually add a new element. Okay, questions? All right, so yeah. I feel like I should have brought up the stack a little bit later. It is sort of relevant because it is, for assignment 3, it is one of the ways that you can do the things that are asked of you. Not the only way, but the other thing that we have to do, perhaps I insert a node. The node is higher than everything in my current list, in which case I'm going to increment this h until my sentinel is pointing at it. So okay, removing is easier because we don't have to worry about the stack. If we remove something and we don't find it, that's fine. Right? We don't have to remove a thing, we just return. But somewhere along the line, I do a search for the predecessor, and somewhere I take a look at the next node and I see the thing, I see the thing that I want to remove, which is this 2.5, in which case I just take, if this is u, I say u.next equals u.next, right? And that takes this pointer and points it over here. Of course, these are all at the current height. Yeah. Very simple. I go down the search path. If I see the thing I want to remove, then I execute this line, and that's about it. So we don't need a stack in this case. We can just, as we search for the predecessor, we remove it. Once we see the node, we just stitch it out. So yeah, it really is, I keep walking to the right, and then I check to see, if the thing that I'm looking at is the thing I'm trying to remove. And if so, I'm going to, remember that I am actually removing this thing and then stitch it out just like this. There is the edge case, of course. If the thing I'm removing is the highest thing in my list, I have to decrement the sentinel. I have to decrement the height. But yeah. And then at the end, if I remove something, I decrement n, and I return that. Questions? Okay. Yes, so this is the example. If I had something, I'm removing something and it happens to be the highest thing. Well, as I'm removing it, if this is pointing to null, then I know that I have to decrement my sentinel, right? So that's what this statement does. Or sorry, I have to decrement the height. Okay. So that's basically the operations. Again, if you're confused about some of the stuff, like the stack, for instance, just remember everything relies on that find, right? I have to find the predecessor. As I'm finding the predecessor, I just make adjustments to every linked list I see along the way. And then there's some edge cases with the height and stuff like that, but that's sort of less important. The claim is that all of these run in log n expected time per operation, right? They all rely on the same process of find. Otherwise, they're just moving around a few pointers. So yeah. We'll prove that a bit later. Questions before we continue? Okay, so The other thing we're going to look at is we did mention that this makes a nice random access list. We're going to see how much faster it is than, for instance, an array list. So I want to take that same basic structure and I want to implement these methods. Of course, now these are no longer values. These are also indices, right? So this is, maybe I'm storing ints, and it just so happens that I'm storing 0 at location 0 and 1 at location 1, and so on and so forth. So this is a linked list with indexes, which requires a slight adjustment, right? And the reason why it requires slight adjustment is, well, maybe I'm in list 5. I take a look to my immediate right. I know if I'm at the sentinel, I'm basically like this is 0, so we'll call this -1. I look to the right. What index am I looking at? Right. So that's, I don't know. I know the value. I can see the value, but I don't know how many places that I've skipped. Right. So there's a couple things we could do. We could store, like I could say, well, I could put an extra field in this node and say, well, this is index 4, and this is index 5, and this is 3, and 2, and 1. And that would work, except now if I add something at location 3, I have to go and I have to change this to, if I add something at location 3, I have to change this to 4, I have to change this to 5, I have to change this to 6. I basically have to do, again, O of n operations, and I've lost, even though my find was really fast, renumbering all those indices is going to be slow. So I don't want to do that. I want to compute the index as I walk through the list. Okay, so now on my find path, I'm going to keep track of some extra counter. We'll call it j. J is the current index. J starts at -1. And then each of my pointers, I'm going to store some extra information, right? So here I'm going to say, well, if I'm looking to the right, my next pointer points to this node, but I also want to say, well, this has length, I believe it's 5, right? So 1, 2, 3, 4, 5. So I'm going to store some extra information for each of my next pointers, right? So this points to a node, but I have a second array that has, that's a bunch of integers, which is the length of that, of the path. Right, so now my skip list looks like this. Each of these next pointers carries with it some extra information, which is the length or the number of things that I'm skipping, or the number of steps until I get to this, this next node. Okay, questions? All right. So my node changes again, just slightly. I'm going to have an array of integers that keeps track of the length of each of these paths, right? So if this was the sentinel, then this would have length 5 and 5, and then whatever else was down there. 5, 5, 3, 3, 3, and 1. Okay. That's going to be implicit. We'll just write it on our diagrams like this. We're gonna work a lot from the diagram. We'll glance a little bit at the code, but all right, questions? Okay. So we know what the find predecessor looks like. Now our find predecessor is slightly different. So it used to be I looked from here. I was trying to find some value, and I compared the value I'm looking for to the value at that node. And if the value I was looking for was less than or equal to the value at the node, I go down. But here I want to compute the index, right? So I know my current index is not -1. I add 5 to -1, so j equals -1. I look to the right, I say plus 5 is equal to 4. So I know that this is index 4. And then I say, well, I'm looking for an index, right? I'm looking for the predecessor of 4. So find pred of 4. So is the thing I'm looking at less than the, is the thing I'm looking for less than the thing I'm looking at? I think I'm saying that wrong again. If I'm looking for 4, I want to find the predecessor. So I compare my, my current index plus the length. I compare it to I. And if I is less than or equal to 4, then I go down. All right, so that's it. Right, so in this case, I start at -1, I add 5, it's 4. I is equal to 4. So since I is less than or equal to, since I is less than or equal to the thing I'm looking at, I go down. Again, I look to the right. I'm still at index -1. I add 5. I'm looking at index 4. And I'm looking for the predecessor of index 4. So that means I have to go down. Down here, the length is 3. So I add 3 to -1, I get 2. So I know I'm looking at index 2. And that is less than 4. So I'm going to go to the right in this case. And when I go to the right, I add 3 to j, right? So now j is equal to 2. All right, so j always contains the index of the current node, and then I add the length. When I look to the right, I add the length to it to see the index of the node I'm looking at. I compare it to the thing I'm looking for and decide if I should go down or move to the right, further to the right. Okay, so the same essential process as in our sorted set, but instead of, comparing the value that I'm looking for to the value I'm looking at, I'm just computing these indexes and comparing them that way, right? Otherwise, pretty much the same process. Yeah. So the big change to this is this used to be the c.compare, or x.compare to whatever the node is. And then we check to see if it is less than 0. But now we just make sure that the current index plus the length of the current edge we're looking at is less than the index. Then we want to move to the right. Otherwise, we want to move down. And if we move to the right, we also update the current index. Okay. Questions? All right. So this is essentially the finding the search path. So let's go through. Let's go through it once in its entirety. If I call get4, so I have I is equal to 4, and my current, I should work on my handwriting. I is equal to 4, j is equal to -1, r is equal to 5, right? So r is the current height. So I say, well, I'm at this location. I look to my right, so it means I add the length 5 to j. So j plus 5 equals 4. I compare that to the thing I'm looking for. It is not less than the thing I'm looking for, so that means I decrement the height. I look to the right again, I find the same thing. J plus 5 is equal to 4. It is not less than the thing I'm looking for, so again, I decrement the height. at 3, now I have j plus 3 equals 2, which is less than the thing I'm looking for. So I'm going to step to the right. J will get updated to 2. J plus, I'm looking to the right. So j plus 2 is equal to 4. That is not less than the thing I'm looking for. So I go down again. I look to the right. J plus 1 is equal to 3. That is less than the thing I'm looking for. So I go here. And then I update my j to 3. And then, well, this is 4, and I'm done. Okay, so that is the process. Going through in a little bit of extra detail here, not to try to bore you, but yes, the numbers on the arrows are the number of, it's the number of steps until the next index, right? That's basically it. Is it the same as the number of skipped ones? It's the number of skipped ones plus 1, I think. But yeah, this is sort of the stuff you'll be dealing with on your assignment 3. Okay, so just wanted to go through an example. All right, questions? Okay. Okay, so again, find predecessor. If I have find predecessor, I can implement get. So I got to do a bounds check, obviously, right? So I'm keeping track of the number of things in my list. So like any other list on my get, if I try to get something out of bounds, I throw an exception. But I don't do a null check here, right? So previously on my find for the sorted set, I made sure that this wasn't equal to null. But here I don't care. Right? Find pred is going to return a node. And well, if I was in the proper bounds, then I know that this node is valid. And I know that the next node is going to be the node at index I. Right? So unlike sorted set, I don't have to do a null pointer check here. I know I have a valid node because it's in the correct range. All right. Set, again, almost exactly the same, except instead of just returning the thing that I find, I want to set it. So I store u, I store the old value, I reset the value at u to the new value, and I return the old value. Right? Both of these rely on the find predecessor function or method, which we claimed was big O of log n. We're going to prove that, loosely speaking, a little bit later. We'll sort of get the intuition behind it. But. All right. Adding to a list is easy because if I add at a certain index, I don't have to check to see if that index exists. I already know that index, if it exists or not. I'm inserting something new every single time, right? I don't have to, I'm allowed duplicates, so I don't need the stack. I just need to walk through. There is one additional detail, right? So I'm at my list 5. I look to the right. I look to the right. So -1 plus 4 gives me the index of 3. And I wanted to, this is a call to add 3. So this is, in some sense, too far. I want to add just before this node. But, so I want to go down, unless the new node I'm adding is high enough. But let's say that this new node is here. So I look at the new node. I don't have to put it in this list, but I do have to, I mean, this used to be 4 from here to here, but now I've added another index, right? So before I go down, I want to change the length of this to 5. Right? So every time I take a step down, that means that I've looked at something that's going to be to the right of the thing that I'm adding, which means that the length of my path from my current node to that node is going to be increased by 1. Okay, so I have to change the length as I go down. So we can see that here, and we can see that here, and we can see we started to do it here. So let's take a look at what we did. This goes to 5, this goes to 5. This one I'm okay. I didn't take a step down, I took a step to the right, which means that I'm safe because I'm not inserting here. Here I look to the right. The thing I'm looking at, I keep track of my current index. J is equal to 1. 1 plus 2 equals 3. This is a call to add at 3. So yes, I'm going to go down. Before I do that, I want to increment this to 3. But aha, I'm not done yet because I still have to put in this new node. And so I have to do a little bit of very sort of simple calculation, but I have to figure out, so I look to the right, I know the new index of this is 4. And I know I'm adding at 3, so as I change these pointers, I can compute that, yes, this should be 1, and also the total length of this path is 3. That means if this is 1, I have to subtract 1 from here, and this goes back down to 2. Right? So before I step down, I increment, and then I have, again, this goes to 3. So I know the total length from my current node to the node I'm looking at is 3. But now I'm going to insert this node. So I have to say, well, I'm looking at index 4, I'm adding at 3, that means this must be 1. And if that's 1, then I have to subtract 1 from this, and this has to be 2. Okay? So again, the code is written for you. You're going to have to adjust it a little bit, but just to show you what's actually happening, we increment it first, and then if we are inserting in that location, we have to divide up that length into whatever comes after the node and whatever comes before. All right, questions? All right, so then you get some process that looks like this, right? So these are both incremented, that's fine. These are incremented, and then I was at 3, and I split the 3 between this and this, right? So whatever's after the node and whatever's before the node, those lengths should add up to whatever the length was before, which is 3. Okay, and this is sort of the code for it. Again, this part's all very simple. It's just a search path. Here is every time, down here, this is r minus minus. But before I do that, I increment the length of the path. And then I step down into the next. But before I step down, of course, I have to check to see if the current node I'm trying to add is going to be added in this list. And if it is, I redirect the pointers. This is just a singly linked list operation. And then I have to adjust the lengths, right? So I take the current length and I divide it between the 2 nodes. I'm not going to go into detail here about exactly how if you take a look at the diagram and sort of match it to these things, you can figure out exactly what's happening here, right? But basically, I minus j is just going to be this, and this is my former length minus this, so that gives me the 2, and then this gives me the 1. Yeah, of course, that's easy to say. It's another thing entirely when you're trying to program it, but questions? Okay. Yeah. I was gonna, I think we were hitting enough detail here. So now, if I want to add, so this is right, so that this add function adds a node at index I. So if I want to add a node at index I make a call to add ix, I make a new node. If the height is higher than the height of my skip list, of course, I adjust the height, and then I make a call to this add node, which does all of these operations. Okay. Removing is similar to adding, but we only decrement. We need to decrement the length of at each step, right? So again, I'm here. I look to my right. This thing I'm looking at, I want to remove whatever's at location 3, which is here. So the thing I'm looking at is, of course, further than the thing I want to remove. So I'm going to step down. But of course, before I do that, I want to decrement the length because I know I'm eliminating this one node, right? So I'm going to, even though I can't see the node that I'm eliminating, I still have to decrement the length of the path. And then I go down, I do that again. Here, the thing I see is less than the thing I'm removing, so I go to the right. Yeah, what is this? So this used to be 2. I'm removing that, so this goes down to 1. And then I'm going to, well, when I remove that, this used to be 1. So 1 plus 1 is equal to 2. So the new length is 2. Just really the opposite of the add, where with the add, I split the distance, right? I had some total distance here, and I split it up between here and here. Now I have 2 distances. I have 1 and 1, and I'm just going to add them together to be 2. Okay, so I'm just going to take the 2 paths and sort of connect them. All right. And that's, yes. So again, the length of my paths, every time I go down, I decrement. And then before I go down, I check to see, well, do I have to remove from this current path, right? This is the thing I'm looking at the thing I'm trying to remove? And if so, I store that value. I stitch it out. I update the length. And then if I have to, I decrement the height, but then I go down. All right. I feel like this is a lot of detail. Okay, so the theorem for the skip list is that I can do all of these operations in log n time. And again, we got kind of complicated there. So the takeaway is the find, right? I'm looking for something. So if you know how to do the find path, the find predecessor, and then with the skip list, you also have to update the lengths, which is a little bit, are we required to know how to program it? So I'm giving you the skip list starter code, and I'm going to talk about what you're going to implement. You're going to have to adjust, you're going to have to basically adjust this code, right? Yeah, all right. I mean, let's talk a little bit about the assignment and what I expect you to do. So you're going to have a skip list, and you're going to do, there's 2 main things, and then one sort of, well, I guess there's 3 things. One is you're going to take 2 skip lists, and let's make some very tiny skip lists. Right, and I guess this would be the sentinel. And then I'm going to ask you to append these, right? So at the end, so this is my sentinel here, and this is my sentinel here, and I have 2 items in each list. And this we'll call list 1, and this we'll call list 2. I want you to be able to append list 2 to list 1, and you can destroy it in the process, that's okay. So this sentinel is going to be gone. This will now be part of the new list. This sentinel, the height will have to be adjusted, and I end up with 2 lists stitched together in log n time, right? So it has to be done quickly. So I could, for instance, take list 2, and I could remove everything from list 2 and add it to list 1 at the proper index. And that will be correct. Well, I'll also be looking at the height of your nodes. But you could write code that'll do that. But it won't be fast. So you want to be able to, in some sense, stitch it together as fast as I would add something to this list, right? But instead of adding one thing, I'm going to add any number of things. And then, well, the other thing is you're going to do the opposite of that. I'm going to take 2 lists and say, well, I want to, this is 0, 1, 2, 3. And let's call us, I don't know if I call it split, but I'll split at index 2, which means that this is going to return a new skip list that looks like this. And my old skip list will now look like this. So I want you to take 2 skip lists and put them together, or take 1 skip list and divide them into 2, and both should happen very quickly, right? It's log n time. The same amount of time it takes to add and remove. Maybe after the exam break, we'll talk maybe in a little more detail. Maybe I'll have a few more questions about it, but yeah, that's essentially. The last thing is there's a visualizer, which I'm going to show you guys. Maybe I'll show it to you guys and then we'll go on break. You're going to update it to show me the last find path. So yeah, let's demonstrate that. So this is code written by Robert Collier, which I have asked his permission before, not this year. I think I'm grandfathered in. I don't want to bug him every single year that I use it. So use with permission and adjust it a little bit. But basically, he wrote a skip list implementation. This is not the implementation I'm going to give you. I'm going to give you the actual skip list implementation with a few extra features. But this is Robert Collier's version, and it only stores characters, which actually the one I'm going to give you will also only store characters. It'll make things easier. So we have add character, we have add new node. So this is sort of a simplified version. So we have a find, we have an add last function basically. But it's enough to be able to construct and search through a skip list. So we make a new skip list, we add a bunch of characters, the letters in skip list plus a few others. And then we print out the skip list, and then we search the skip list for P. And when we search the skip list, it will give us the path. So yeah. So yeah, we have A, D, I, K, L, T, S, T. Right, so, oh yeah, sorry. This is the skip list set, right? So these are in sorted order. So we added skip list plus A and D, and it put them in sorted order for us, and it drew out sort of the structure of the skip list. And then we called find predecessor node for P. So searching for P, we saw in list number 2, we saw K, so it went here. And then in list number 1, it saw K, so it went here. And then in list number 0, it saw K. And then it finished a little prematurely, but okay. Well, there's a small bug in this code. That's okay. Yeah, it should have ended at L. Okay, well, that's pretty close. We run it again, we get a different shaped list, and then the search path is the Sentinel and L3, Sentinel and L2, the Sentinel and L1, and then we go to A, and then down to I. Maybe I'm searching for, am I not searching for P? Yeah, there's a little bug in the code. I and, oh no, so it went down to I. Okay, so yeah, that's it. It just, once it gets down to L0, it stops for some reason, but yeah, it should actually add the rest of these. Okay, so a couple things about this piece of code, which you're going to play with something very similar. A couple of tricks you can use. So this random, right? This is all built randomly. So here I make a new random object and I initialize it with system at current time milliseconds. So if you are testing, it's possible you want to do something like this. Give an actual seed value. So this current time milliseconds will give you a random seed value. But if I give the same seed value, then well, we can see I get this list, and then if I run it again, I get the exact same list, right? So if you seed the random value, when you rebuild the list, you'll get the same thing every time. So if you're trying to, for instance, reproduce an error, that might be a good idea. One of the things you could do. But yeah, so there's also, let's see, Skiplists list demo. Yeah, okay, so one sec. There's also that's the set version. There's also the list version. Yeah, so the list version, there's two print functions, right? So one prints without the lengths, and this one prints with the lengths. So again, you can use these. The version I'm going to give you will have these, and you can use these for testing purposes, right? So when you stitch together two linked lists or two skip lists, you should get something that looks correct. The last thing I'm going to ask you to do is, so here we can see that it highlights the search path, perhaps not quite, I mean, there might be a bug in this. Regardless, I'm going to ask you to update this to highlight the search path. And basically, you're going to change these into so instead of this, you will do this. Okay. So every one of these arrows, if it's on the search path, should look like that, with the numbers embedded in the middle for this one. It's harder than you'd think. So yeah, that's again, I still have to write up the spec and I still have to write the tests, but I'm pretty sure, 99% sure that's going to be it's going to be your assignment 3. All right, questions? Okay, we'll take a break. We'll come back at 1 or a little or shortly after, and we will start talking about. We'll talk about the midterm. So we'll briefly go over the midterm and then start on hash tables. Yeah. Okay. So yeah, 103, close enough. I did say we're going to talk about hash tables next, but I am going to talk about skip lists a little more. We're going to do the analysis. There's some math. You don't need to know the math, but I'm going to tell you the intuition behind why they perform so well. But before we do that, we're going to talk about the practice midterm. Okay, so of which skip lists are a part. But to start, we can operationally define a fundamental operation, right? So we talked about when we're analyzing an algorithm or a data structure, we talk about fundamental operations such as copying a piece of data or accessing a piece of memory. So for the purposes of this question, if I copy a single piece of data from one location to another, as I would an array, right? So an array stack, for instance, if I add in the middle, I have to move things, and that's a copy operation. So each of those would be considered one fundamental operation. Or if I have a linked list, right, and I want to get the node at location I, then on a singly linked list, I would have to start at the head and take I steps before I got there. So those are all fundamental operations. What we're trying to do is we're asking you basically if you understand the runtime of these data structures, right? Do not give big O notation, and it's rounded to the nearest 100. The reason why it's rounded to the nearest 100 is because I don't care. I'm not interested in like off by one. If it's 99 or 101, I don't care. I care that you understand how these data structures work in a asymptotic way, right? So in terms of basically, in terms of n, but not big O, please. So let's answer some of these questions. So calling add 800x on a singly linked list, how many fundamental operations rounded to the nearest 100? Singly linked list. So how many steps do I have to take before I get to location 800? What's that? How many steps? Yeah, 800, right? This would be 800. Right, I start at the head. And this is location 0, 1. Head points to 0. And I keep going until I get to the 800th node. And then it's a singly linked list, so I have to start at the head. I can't start at the tail. So yeah, is that clear? Is there any questions? Calling remove 700 on a doubly linked list, right? So there's 1,000 elements in my list. If I call remove the element at 700, how many fundamental operations is that? Yeah. Sorry? Yeah, 300, right? A doubly linked list, I can start at the back. And so if you take what you know of doubly linked lists, yeah, let's just pretend. So this is location 1000, this is location 0, but I have a dummy node that can access. And so I'll check and see that, well, 700 is closer to 1000 than it is to 0. So I'll start at 1000 and I'll take 300 steps backwards to get to that location, right? So that's 300. Call get 100 on an array stack. Sorry? Say 1? Yep, 1. Yeah, it's an array stack, right? I have random access. I can get really quickly. So I would round that off and say 0, right? Round it to the nearest 100. It does say to round 1 down to 0. calling add 200x on an array deck. Again, it's 1,000 things in there, right? So when I add, I have to move 200 things out of the way, basically. And I'm closer, right? So I have an array deck, and somewhere over here, there's location 200. I'm adding a thing, and I have to shift 200 things in order to add it. So yeah, this is going to be 200. Add 400x on a dual array deck with front size 300 and back size 700. How many fundamental, a little bit of math here. How many fundamental operations? So a dual array deck is 2 array stacks back to back. And we say there's 300 here. And 700 here. And so index 400 would be at index 100 here. And then I would have to, that means there's 100 to the left, 600 to the right. It's an array stack, so everything has to be moved to the right. So there would be 600 fundamental operations. Okay. This just tests your basic knowledge. So it's one thing to memorize the big O notation, but it's another thing to actually apply it. So we're asking you to apply it, right? Yeah, questions? Yeah. Yeah, no, you can ignore, ignore stuff like that. Yeah, it's a good question, but no balance, no resize, just to get set, add, remove. Yeah, you're right. I will, that's a good point. Yeah, no resize, no rebalance or anything like that. Okay, so yeah, and any probably maybe not. These would be simple ones, right? So probably everything you see here. I'm trying to remember what else we did. If anything else would fall into that. There's going to be a coding question. Don't understand why it's 600. Okay, oh, it's a good time to ask. So again, I'm adding at index 400, right? So index 0 is in some sense here, and index 300 is, well, give or take, it's here, right? It's probably in the next one, but and let's say this is 301. This is why it's rounded to the nearest 100, because I don't care about these little details. So from 300 up to 1,000. But this is an array stack, and this is 0 to 700, right? So there's 700 things being stored. The array stack indices are here, 0 to 700. But our dual array deck indices go from 300 to 1,000 or whatever, roughly speaking. An array stack, it's not an array deck, right? So I'm adding something here at location. Sorry, this number is confusing me. I'm adding something here at location 400, which corresponds to location 100 on my array stack. And in order to add on my array stack, if it was an array deck, I could move these guys, but because it's an array stack, I have to move everything from 100 to 700 one space to the right, right? So then I would have something at 700 would move to 701, and then 699 would move into 700, and then 698 would move into 699. And I would do 600 of these copy operations to make space for X at location 100 on my array stack or 400 on my dual array deck. Yeah, hopefully that makes sense. All right, perfect. Okay, so there will be a coding. This is array deck, right? So this means this is the modulus operator. I'm not going to write the add. A couple things to keep in mind. The array deck, we have a value j that points to, right? So an array deck is a single array that I have a bunch of data elements, maybe somewhere in the middle, or basically they start at some arbitrary location. So let's call that j points to the start of the data, and then the data goes to the right up to location j plus n, and possibly, it's possible that I have j here and that I add data and I wrap around and j plus n is here. We do everything modulus the length of this array. Right, so what that means is that when I'm adding something at location I have to do, for instance, well, let's say it was set I, since that is a little bit easier. I would say, what did I call it? A at, so j plus I mod a dot length. Wait, is that what I called the, oh, I called it array, sorry. Well, whatever. Array A in this case. So this would be my set operation, would be that, right? After I check to make sure that it's in the proper range, right? So that I is between 0 and n minus 1. Then I can, yeah. So you have to review the array deck if you're not familiar, and review modulus and how we do all that. And then if I'm writing the add function, well, then of course, before I do this, I have to loop through and I have to copy everything out of the way, right? So the code is on the textbook. It's also, sorry, it's in the textbook. It's also on the slides, or in the ODS Java library. You can see it in any of those locations. I'm not going to be very pedantic about syntax, but you do have to communicate these ideas, right? That you're using the modulus and that you're copying things in the correct direction. If you're off by one for the for loops, again, you're not going to be penalized for that. Only really egregious logic errors. But yeah, questions? I might also, instead of an array deck, it might be a dual array deck where you have the two stacks. Right, that would be in some sense a little bit easier, although it does, because this is, let's face it, there's a lot of technical details here. A dual array deck, there's fewer technical details, but you do have to make some calls to the underlying array stacks. So do make sure you know both of those things. Questions? Okay. Rootish array stack. So how do I index into a rootish array stack? We'll give you some hints here. So I'm going to, for instance, call get 746. And inside, there's going to be some, is it a get location? Is that the rootish array stack? Which is going to return, no, sorry. There's not a get location. That's the next one. But I'm going to have my block index is equal to index to block of I. So I want to know what this function returns, which block I'm looking at, and then the index into that block. So int j So yeah, how do I compute that, right? So block B and J, where B is the block index and J is the index into the block, right? So again, if you recall the root-ish array stack, I have a list of primitive arrays. Each array is one bigger than the previous. And then, so yeah, there was some fancy math on how to get the block. And I even tell you, it's the smallest integer b such that this is true, right? So we went over why, that because basically, if I say 1 plus 2 plus 3, basically I keep adding those together until I get to a value that's greater than or equal to I plus 1. And the plus 1s are there because we start all our indexing at 0. But otherwise, it's just, I'm just adding up. I say, well, you know, I'm looking for 746, so 1 plus 2 plus 3, until I get a value greater than 746, and then that's the block that I have to return. And you can figure it out using this equation. So there's a couple of ways to go from here. But any questions so far? Sorry. Okay. So you can do guess and check. You're allowed a calculator. So I plus 1, 746. So I plus 1 is equal to 747. So I want to find a value b that I plug into this equation, the smallest value that is still greater than or equal to 747. Okay, so you can do guess and check. I can take a calculator and say, well, let's guess that it's block number 20. Just so whatever. So that means 21 times 22 over 2. And if that is at least 747, then you know, I know I'm in the right ballpark. 21 times 22 divided by 2, 231. So really not even close, right? So that is way under 747. And so you can keep guessing and checking until you find the right value. The other thing you can do is just jump to the notes. And one thing we talked about is, well, how do we solve that? It's a quadratic equation, and you can, if we look at some of the previous slides, right? So this is where you replace J with B, but this is the equation that we were looking at. And you can reduce that to a quadratic equation that you solve with the quadratic formula. And so I can get the exact block by using this formula. I'm not going to give you that formula, but if you want to memorize it, you can. So the block would be I is 746 times 8 plus 9. And then I want the square root of that. So 77 plus -3, so -3. And then divided by 2. And I get 37. So it should be block 38. Right? So 37 point something rounded up is 38. Okay, so I go back to, I should, B equals 38 should give me a good value. So I can double check to make sure that gives me something greater than 747. So that's 39 times 40 over 2, which is 39 times 20. And 780, which is above 747. So yeah, it seems it passes the sanity check, right? And I'm guessing if I tried 38 and 39 divided by 2, it would not be enough. In fact, I know it would not be enough. Okay, so B is 38 in this case. How do I get J? Well, I just I minus B plus 1 over 2. Right, so B plus 1 over 2 is, well, (38 times 39 over 2, which is 19 times 39, 741. So 746, J would be 5, right? And if this doesn't make any sense to you, then just study root array stacks, right? Questions? So yeah, this is what we went over in the notes and on how to make it. The last thing is the skip list. Please read carefully. All right, so I might actually change exactly the specification here, but it does say that we're going to construct a skip list. How we're going to do it is we're going to flip a coin a bunch of times. So given a singly linked list, we're going to make a skip list, right? So it's slightly different from what I just taught you, where we added things one at a time. We're going to take a pre-existing list and build a skip list. And how we're going to do it is by reading this sequence of coin tosses and applying them to each of these nodes in turn, right? So in some sense, I start the first coin toss as heads. So heads means I promote A here, right? So, and we will list the coin tosses. Actually, let me list them with H. Okay, so that's that one. Heads, I go to the next one in order. That means I promote B as well. Next heads goes to C. I promote C. Next heads goes to D. I promote D. Tails goes to E. I don't promote E. Heads, tails, tails. Well, let's not get ahead of ourselves. So heads, I promote, tails, I don't, and then I start over again. So the next one is tails here, which means I do not promote this. So this is list number 1 now. List number 2, after tails is heads. So that goes here. So this guy does get promoted, but I'm only looking at now everybody in list 1. So for instance, heads, heads. I have tails here, but I'm going to ignore E because there's no, the node E is not in list number 1. I'm only looking at what's in list 1, number 1. So this would be tails over here. So this is heads, heads, tails, which means I do not promote F into list 2. And then heads, I'm going to ignore G as well because G is not in list number 2. So now I want to look at who to promote into list number 3, and I'm just looking at these 3 guys. These are the only ones left in list number 2. So I keep reading here, heads, tails, tails. So this promote here, but tails, tails, those guys don't get promoted. And then heads, I get promoted once more, and then tails, I'm done. So my skip list would look something like this. I may have made a mistake because I was being sort of careless there. Just be careful when you do it. Is the procedure clear? Any questions? Okay, so this is just testing your, I mean, this shouldn't be hard. As long as you read carefully and do it exactly, follow the instructions, you just make a skip list, and then you find the, well, what's the height? The height is 4. So every time, so I start by promoting into list 1 by looking at everybody in list 0. list 0 is everybody. When I start in the next list, so when I'm looking at who to promote into list number 2, I'm only looking at the ones that are in list number 1, right? So these guys, I will ignore them, and this guy, and I will ignore them. So my new coin flips, I only apply to people that are in list number 1. And then, when I want to figure out who to promote into list number 3, I look at who's in list number 2, which is this guy, and this guy. So just those 3 are eligible for promotion. So I apply the coin flips and see who gets promoted into list number 3. And it turns out it's just this guy. And then I look at who to promote into list number 4, and it's this guy one more time. So yeah, hopefully that's sort of clear. Yeah, yes, you should. At the end of the day, this should be the same height. Right, because the next thing I'm going to ask is for you to find a search path on this skip list. Okay. So what is the height? The height is, these don't quite match up, but if I drew them correctly, it would be L1, L2, L3, L4. So we started L0, so the height is 4. And what is the search path? What is the length of the search path for finding G? And then the instructions are to find G directly, although in this case, it's the predecessor plus 1, which means that my search path would go 1 step here, 2 steps, 3 steps, 4 steps, 5 steps, 6 steps, and then 7 steps, 8 steps, and then 1 more step into G, right? So finding G directly instead of the predecessor. Again, please read the instructions carefully on the day of, right? There is I suppose a chance. I'll probably leave it as is, but I might change it, I guess, if I think it would be more clear or more useful to change it, I will, but all right. All the nodes on the search path in the order they were visited. So, well, let's see, it was the Sentinel. We jumped to B, and then C, and then D, E, F, and G. So we only skipped 1, but yeah. All right, questions? Yep. Yeah, you'll get marked on whatever the skip list you created, if you can find the correct search path on that. Yeah. So you don't get penalized. You won't get penalized twice for making a mistake on that. That's a good question. But yeah. Other questions? Okay, that's about it. This might get updated. If it's updated, I'll release an announcement. If I decide to add a question or change some questions. Again, it's 80 minutes. Probably that's going to be it for the day. I'll let you guys go after that. I'll see where we get after today. Let's say for now, there's no lecture after the midterm. If that changes, I will update you shortly, right? As in shortly being tomorrow. So yeah, expect 80 minutes, and then you guys can go and prepare for any other exams you have, and or enjoy your summer a bit. All right. Yeah, either the dual array deck or the array deck. I'll limit it to that. I don't expect you to memorize all the code for every single data structure that we've seen. I'm really looking for I'm more interested in big ideas, but it is important that you know a little bit of coding, right? So, okay. Let's see. So we are gonna analyze skip lists. I don't want to beat you senseless with all of these details, but I do want to give you a sort of an idea of why the skip list works, right? So there's going to be some math. I will explain it a little bit. If you don't get it, that's fine. I'm going to explain the big picture stuff, and hopefully you get that. So yeah, Felix von Leitner, I guess. If a data structure can't be explained on a beer coaster, it's too complex. My goodness, I mean, that's a lot of data structures that we're looking at are, I mean, there's something to be said for that, right? Array lists perform pretty well in practice. A lot of the stuff we're looking at are very niche data structures, but sometimes you need a niche data structure. So in this section, we're going to look at the expected height of the skip list, the expected size in memory, and the expected length of a search path. The expected height is simply, it contributes to both the size and the expected length of a search path. Yeah, so we are going to, the expected length of a search path, because basically everything we do depends on that search path, right? Whether we're finding, adding, or removing, that basic find predecessor operation is fundamental. And they're built randomly, so we're going to look a little bit about, it's not useful to look at the worst case, because when we build things randomly, we expect them to be sort of average. So this is going to be based on expected values. Again, expected values are just weighted averages, average weighted by probability, right? So for instance, a lot of the randomness in skip lists is closely modeled by the coin toss. The coin toss determines our height of our nodes. So let's say I flip a coin and I get heads with probability 0.5 and tails with probability 0.5, then I keep tossing the coin until I get heads. So how many times do I expect to toss it? And we said on average it's 2, right? I kind of mentioned that earlier. So sometimes I get heads right away, and then the number of coin tosses is 1. Or I get tails and heads, or I get tails, 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 heads, but this is kind of rare, right? And well, this happens. How often? How often do I just get heads? Maybe that's not a really well-defined question. If I perform this experiment 1,000,000 times, how many times would I expect to see the length of 1? Yeah. Yeah, 500,000, right? About half. Because when I flip a coin, it comes up heads with probability 0.5. So I'd expect about half of them to have a length of 1. So in a skip list, about half of my nodes are going to have a height of 1, and the rest are going to be somewhere else on this from height of 0, and the rest of the nodes will have somewhere a height of 1 to infinity, right? Not really infinity, but in any practical sense, it's going to be limited by 32, because that's the number of bits in an integer. But yeah, so on average, we expect tails, heads, and this is the math behind it. Again, you don't have to understand the math, but just know that if we looked at all of these cases and averaged them out, on average, we get 2 coin flips. Okay, so some of them are going to be, some of these experiments are going to be very long, but they're going to be very few of them. And the same with when I look at the height of my skip list, most of them are going to be pretty short, most of the nodes, but occasionally we're going to have nodes that are a little bit higher than average. And that's exactly what we want. So we use indicator random variables if you're interested in this. So here's this sort of high level. Yeah, I don't know if maybe I don't even want to get into this. If you're interested in indicator random variables in this analysis, you can come see me after. and we can talk about it. The math is here if you want to look at it. But again, I want you to, the more important thing is that intuition, right? The average height of a node is going to be 1. The average node will look like this. Half of them will look like this. And then there's going to be a few that go a little bit higher, right? It will happen, but they'll be seldom. And we'll say something a little more concrete about that in the future, but yeah, so this is the average case. That's all this is saying mathematically. Okay, questions? Okay, so now that we know the average case, we can figure out about how much space we expect our skip list to take up. So we're going to prove that 3n plus log n plus 3, I was thinking about this. This is not even quite accurate because I'm not counting pointers. So we're ignoring pointers. There's n pointers as well that I'm not counting. But I have, of course, n pieces of data. And I'm going to show that, well, on average, there's 2 n pointers. So what do I mean by pointers? Right, so this is my piece of data. I have n of those, obviously, because I have n pieces of data in my list. And then for each piece of data, on average, I have 2 pointers, 2 next pointers. Right, which is what we just showed on the previous slide. So if we took the average of the number of next pointers over our entire list, we would get basically the average node is, of course, 2, by the same argument that we used before for the coin flips. So each node has on average 2 pointers. There are n nodes, so that means I have 2 n pointers. Okay. Again, if you're interested in the math, I'm happy to go over it with you. It's a little advanced for a class that does not have a prerequisite of 2804. But yeah, questions? Right. Again, high level, each node on average is 1 piece of data and 2 pointers. So that gives me 2n for the pointers and yeah, so n nodes and 2n next pointers. So that means just in this area alone, I have 3n pieces of data, right? N for the data and 2n for the pointers. But I haven't counted the sentinel. So how much data is taken up in the sentinel? Well, it depends on the height, right? So the sentinel is the maximum height among all nodes. And we're going to call this big N. So what I want to figure out is what's the average height of a skip list on n nodes? And it's going to be some function of n. And in fact, it's sort of easy to derive. Yeah, so we can consider the height this way. It is the largest value h such that list number h has at least 1 element in it. Again, we're going to do it mathematically, but before we do it mathematically, I just want to argue this a bit informally. So what's the expected height of our skip list? Well, we start with just a regular linked list, and similar to what we just saw in the midterm, instead of doing the coin flips individually every time I add something, let's say, well, statistically, it's the same as if I just take a full linked list and then flip coins to promote these nodes into higher lists. So given that I flip a coin for each of these, heads, tails, heads, heads, tails, tails, and it comes up heads with probability 0.5, then I would expect to see about half of these nodes in list number 1. Right? Does that make sense? I flip a coin. If it comes up heads, I promote them. If it comes up tails, I leave them just in list number 1. Because about half of my coin flips will be heads, I would expect to see about half of these nodes promoted into list number 1. And then the sentinel would also, of course, be at that height. Okay. So how many would I expect to see in list number 2? Well, again, I can do the same process. I'm flipping the coins. The fact that I'm not doing them one at a time doesn't matter in terms of probability. It's exactly the same. But, so about half, again, I'm going to flip. I flipped heads here and tails here and heads here, tails here, heads here, tails. Now, for each one that I flipped heads, I'm going to flip another coin. And about half of them will come up heads. So this might come tails, heads, tails. And that means that half of them will get promoted. So this guy and this guy. So in list number 0, I had 8 elements. In list number 1, I expect to have 4. In list number 2, I expect to have 2. In list number 3, I expect to have 1. So then I finally, each list has half of the number of nodes as the previous. So how high, if I keep dividing the number of nodes in half until I get to 0, how high do I expect this list to be? So I have n nodes in the first list. I have n over 2 in the second. I have n over 4 in the third. How far can I go like that? Yep. Yeah, it's, yep, log base 2 of n. And that's really the big takeaway from that, is if I continue this process, so here I had 8 nodes, which means I would expect, well, from here it gets a little bit tricky, but let's just say every list that has at least one full node in it, I would expect to have about log base 2 of n lists, right? So I have n in the first and n over 2 and then n over 4, and then eventually I get down to 1, and that's the number of those is log base 2 of n. Okay, so the height is going to be about log base 2 of n. It's a little more complicated than that because, yes, on average, but of course, some of my lists will go higher than that. So I kind of have to count those. So it turns out it's log base 2 of n plus a little bit, right? Plus 2, plus 1, plus 2. But yeah, log base 2 of n, because I basically, each list, I expect to see half of the nodes of the previous list, right? So that's it. The math, well, if I look at all of the lists that have at least 1, and then all of the lists that maybe have, so all of the lists that have on average at least 1 is log base 2 of n, but then sometimes I get lists that are higher, and on average, that this resolves to 1. And yeah, so this resolves to plus or minus 1. For big O, it doesn't really matter, but log base 2, log base n, so log base 2 of n plus 2 is our expected height of a skip list. Okay. And then if we add up, well, the null element in my sentinel, then we get log base 2 of n plus 3. So the total space is 3n plus log base 2 of n plus 3 expected memory, yeah, for our skip list, okay, which is linear. So basically order n. Yeah, questions? Okay, well, this height also comes into play in our search path, because if there's one thing that we know about our search path is that we start at the highest list and we end at the lowest list. So whatever our search path is, it's going to be at least the height of my skip list. So on average, I have to take at least log base 2 of n plus, what did we say it was? Log base 2 of n plus 2. that's just in the downward direction. So what we're also going to show is that the number of steps to the right that I take is about another log base 2 of n plus 1. Okay. And the argument is not that difficult. I'm going to give you again the high level, very high level. So let's see, do I have? Yes. All right, perfect. So we're going to take our skip list from before. I'm just going to draw a very lazy version of it. Half of the elements get promoted into this list. And then let's do a couple more. So yeah, so we have let's say there's 16 in the bottom row and then 8 here. And then we will say 4 in the next. And then 2 in the next. Whoops. This guy and this guy, and then 1 in the last. And so my sentinel will have a height of 4 as well. Okay, so this is, maybe it's better if I do this. Let's say the middle one gets promoted. So what's going to happen is when I start at my sentinel, let's say that it's a perfectly balanced skip list like this. Like I promote everything evenly, I do it deterministically, I don't flip any coins. Well, what's going to happen is that I'm going to take a look to my right. I'm going to see this guy, and I'm going to say, well, is the thing I'm looking for to the right or to the left of this guy? And if I promote everything sort of evenly, then this is about the midpoint. So if the thing I'm looking for is bigger than this, then I'm going to step into this node, and I'm going to skip about half of the elements. And if it's not bigger than this, then I'm going to step down, which means that I will never go in this section of the skip list. So again, I've eliminated half the elements, right? This is sort of, skip lists give us effectively a binary search, right? I take a look, the first thing I look at is the middle of my list, and then I say, is it to the left or to the right, or is this the thing I'm looking for? And okay, so I go down, and then I take a look to the right again. And well, somehow I messed it up, but there should be somewhere, someone at this height. But again, I'm going to take a look to the right, and I'm going to see, well, let's say, I look to the right, and again, I should be looking at about the midpoint of all of the elements that are left, and I'm going to say, well, is the thing I'm looking for over here or over here? And in either case, I'm going to eliminate half of the things. Okay, so which means that my search path, any search path, since I basically eliminate half of the elements every time I take a step, then in my first step, I now have only n over 2 elements to search. In my next step, I now have n over 4 elements to search through. And then eventually I'm going to get down to 1 element, and that's going to be the thing I'm looking for, if I didn't find it already, right? So given that I eliminate half, right? So I start by searching n things, and then I'm searching n over 2 things, and then I'm searching n over 4, all the way down to 1. So there are log base 2 of n steps to eliminate all of the items. Okay, so that's the big picture. And that's if I do it deterministically, and every subsequent, every time I look to the right, I'm looking at the midpoint of everything that's left. But when we do it randomly, we sort of expect, yeah, it's not going to be quite like this, but it's going to be close enough, right? Maybe I don't eliminate half of the elements, but I eliminate a quarter of them. And if I eliminate a quarter, that's still pretty good, right? So that's sort of the idea behind, yeah, those are the big ideas. Again, the height, because, well, I only promote about half of the elements every time I go up in height. And so I can only do that basically log base 2 of n times. And the search path, same thing. Every time I take a step, either down or to the right, I'm eliminating half of the elements. And I can only take about log base 2 of n steps. All right, questions? I think I might touch on the math, but I don't know. This is not a math class. I don't want to get bogged down in that. That's the big idea behind it. And you should understand that. But any questions? Okay. All right. If you're interested, we guaranteed the midpoint? No. So yes, that is correct. We are not guaranteed that. But again, this is average, right? So I'm from here. Sometimes, yes. Sometimes the highest point is going to be the next guy in line. And that's going to not be great for us. And then maybe the next highest is right next to it. And the next highest is right next to that, and so on. If this happens, this is bad for our search path. But this is statistically very rare. And as my skip list gets bigger and bigger, this becomes more and more rare, right? Like if I do this, if I build a skip list on 5 items, maybe I get this pattern. And then maybe every time I search for something, I have to look through all 5 nodes. But 5's not that many. Like for a computer, that's going to happen really fast. If I have a skip list of 1 million things, the odds of getting 1 million things in this order is extremely unlikely. And although we don't do it sometimes on random data structures, if you find you're in a situation like this, you just blow it up and rebuild, right? If things are taking too long, you just rebuild the data structure and you will probably get something better. Okay. Again, this is, so the rest of the slides gets into the math. I'm happy to explain all this to anybody who wants to learn about it or who's interested. I'm not going to get into it too much for this. This is all basically formally what we just talked about, except now we just, we said, well, we're looking at the average now. And on average, you know, it's log base 2 plus a little bit, log base 2 of n. All right. So yeah, add, remove, get, and set all operate in O of log n time. And yeah. All right, questions before we'll look at a quick, we'll see how fast this is in comparison to an array stack. Right, so an array stack, if you recall, well, I mean, we just looked at it as well, but add and remove. If I add and remove to the end, it's fast. If I add and remove from the beginning, it's slow. If I add and remove from the middle, it's sort of slow. So we're going to, we should see drastically faster add and remove to the middle from a skip list rather than an array list. So here's a little test class. We're using, what are we using? Yeah, so we're going to use an array list, which again is just a stack, right? So very slow, slow to add and remove from the middle. Every time we add or remove from the middle, we have to shift half of the elements. But for add, we're just going to, we're going to add at the beginning. Yeah, that's brutal. All right, well, we'll test it for that. So this is very, very bad for an array list. Let's give it a fighting chance here. So we're going to add at the back, which is fast for an array list, but then we're going to remove everything from the middle. And then we're going to test this. So add at the back, remove from the middle. We will do that with both an array list and a skip list. And yeah, skip list. Sorry, just give me a second because I think I have to recompile everything. So I like to develop for this class on Linux, but I'm sort of stuck in Windows because Zoom on Linux is not great, which means I have to recompile everything when I switch from one to the other. So this is called skip list. And what's it called? Skiplist test. Okay, so for the array list, I get three, again, probably tenths of a second or something like that. And the skip list is many times faster than that. This is simply adding to the back, which the array stack is good at, but removing from the middle, which is, it's not that great at. If I don't remove anything, if I just add to the back, I would expect the array list to be faster. I'm just not sure how fast. That's not what I want to do. It's not what I wanted to do either. Yeah, so just adding to the back, which is sort of the specialty for the array list, is 0.289, and for the skip list is 0.395. So it's the skip list is still sort of competitive. And if I do oops, Python 3. So I'm guessing that was 10,000 elements. So I'm going to try it with 100,000 elements. No. Let's do it with 1,000,000. Okay, so the skip list is a little bit slower on average, but not too bad. Of course, when we add and remove from the middle, this will take forever on an array list, I'm guessing. Yeah. I'll wait a few seconds and see if it okay, so an array list can't even really if I have an array list of 1,000,000 items and I remove from the middle until it's empty, it's just going to chug to a crawl, I guess. I think the skip list should be able to do it though. So if we skip the first to do it and only do the second do it for the skip list, let's see if the skip list can handle that. Yeah, so what was taking basically forever for the array list is done by the skip list in, I want to say 0.6 of a second, something like that. So yeah. All right, questions? Okay. So let's talk a little bit about hashing. This will be, so that is it in terms of material that will appear on the midterm. So hash tables and everything after skip lists will be on the final exam. So we're going to start talking about hash tables, and we're going to start talking. So, you know, I had a friend back when I was a student who said that everything worth doing in a data structure, all they needed for data structures was hash tables and array lists. That was his claim. And he's sort of right. I mean, these are two of the more useful data structures. So hash tables. Oh yeah, Patrick McKenzie. So every great developer you know got there by solving problems they were unqualified to solve until they actually did it, right? So don't feel bad if you feel unqualified. That's everybody who did anything worthwhile. But yeah, so we're going to implement an unsorted set, right? So we did the sorted set with the skip list. But if we just wanted an unsorted set, So this is add, remove, and find. How fast can we do it? And it sort of depends on the data, right? So for example, let's say I'm only storing the letters from A to Z. And then I call add A, and I have some data structure here. So where should I put A? I just add it like as a list. I just add it to the beginning. Oh, maybe I add it to the beginning, right? Why not? What if I call add D now? And remember, I want to get it back fast. So where's a good place for D? Should I put it here? I mean, it's still in sorted order, so it's not bad. I could do a binary search on it, but maybe there's a place that's faster. Right. So if I know that I'm only storing these characters, well, there's only 26 of them. And if I think even a little bit deeper about it, these are represented by a char data type, which is 8 bits. And basically, I can represent I can cast it to an integer. Right? It's just a character that is some bit representation. And I don't know what is this? Equal to 48 or something like that in the ASCII code. And then B is equal to 49. So if I can make an array of 26 locations, and then I can say, well, I'm going to take my int. So if I have my character C. If I want to add C, I can add it at my table. I'm going to cast C to an int. And I'm going to subtract 48. Right? So then A will go into 0, B will go into 1, C will go into 2, and D will go into 3. And maybe some of these are empty, right? Because I didn't add B or C, but maybe I added A and D. So there's going to be some empty locations, but the nice thing is that I can find them, add them, and remove them very fast. Real easy, right? As fast as random access, basically. Right? Does that make sense? Questions? So yeah, I can store D there. And basically, so what I've done here is I've developed a hash code, right? So what a hash code is I took a piece of data and I turned it into an index, into a table or a list or an array. And maybe an array because that's the fastest, right? We want random access. But so yeah. And if my hash function is fast, and for the integer or for the characters, it is fast, of course, it's a simple math operation, then all of my add, remove, and find run in constant time, right? So far, the fastest thing, well, the only thing we've seen is a skip list, and it did log n, which is pretty fast, but now it's constant time, if we get a good hash function. All right, so we want to devise some function that takes an arbitrary data type, maybe an arbitrary string, and turns it, I pass it to this function, which returns an int. And this int is an index into some table of n elements. And I want to store them, right? So characters is sort of easy because there's only 26 of them and they really map to numbers. But if I take an arbitrary string, then there's arbitrary number of strings, right? It's like almost infinity. If you want to keep building strings, you can. So how do I'm going to develop a hash function for them, and I can, but it's maybe not going to be quite as reliable as my character hash function. My character hash function, I could guarantee there would be no collisions. But for this hash function on arbitrary strings, maybe I have to compromise on that a little bit. Maybe sometimes I add B and I hash it and it gives me this location. and then I hash a different data type and it hashes to the same location. Okay, so I have a hash function, I put data in, it gives me an index into a table. It does the hash function is very fast, but sometimes two different things will hash to the same location, and that's called a collision. Okay, and so most of hashing is dealing with collisions, right? If we didn't have any collisions, hash tables would be very easy. All right, so yeah, we can devise different hash functions for different data types, and they all run pretty fast, and we get a good distribution where they're mostly pretty random, but we can still, getting something completely unique can be a little tricky. So we have to, in some sense, put up with collisions and have strategies for dealing with them, right? I mean, you could always, you know, if you knew how many data things, you can always make a huge table that could store everything and you'll never have collisions. But of course, there's arbitrary numbers of strings, right? All right, so this is called the collision. And yeah, we're going to develop some strategies to deal with these collisions. All right, questions so far? Okay. So we're going to look at a specific hash function later, a little bit mathy, but not too bad. Again, I just mostly want you to take away the ideas behind the hash function. In the meantime, we're going to assume we have a hash function, and we have some data we want to put into a hash table, but we want a strategy for dealing with the collisions. And so what we're going to do is each entry into my table is going to be a bucket. So we have a bucket array, right? So our table, each entry points to some list of whatever data type we're storing. So every time there's a collision, we simply add the new thing to the list, right? So in this case, hash B equals hash C equals 0. So B and C both go into this location. And when I add both of them, I simply add them to this list. So now I have a list of 2 elements. All right. So yeah, what are the strengths and weaknesses of this? Well, the strength is it's relatively simple, right? Easy enough. I have a hash function, and if 2 things go into the same location, just put them on the list. If I'm bad with my hash function, or if I'm unlucky, of course, I can have a really long list. If my hash function is terrible, I can have basically almost everything in the same bucket. And then I basically have the performance of a list instead of the performance of a hash table, right? So if my hash function is terrible and everything maps to location 0, this will still technically work, but the performance is gone. Now I have to, every time I want to find something, I have to search through this list to look for it. So if the lists get too big, the performance goes down. If the lists are small, if I have 3 items, right, this is okay. I can do a linear search on those 3 items and check to see if the thing I'm looking for is in there, and it won't take long. So yeah, so that means a good hash function that distributes my data as evenly as possible across the hash table is critical. But yeah, also, I mean, the size of the table is going to be also important, right? So I'm storing n items. If I have a hash table of size 4 and I'm storing 20 things, well, that's no good, right? I'm guaranteed to have collisions at this point. So I want to make sure that my hash table is about as big as the number of things that I'm storing, right? So that means on average, yeah, on average, I will have maybe 1 or 2 things in each list, right? As long as my hash function is good, I still might have some collisions, but if the table is big enough, then I can sort of avoid some of that. All right, so T is going to be our table. It's going to be some table of some list And then we have an n, an integer that keeps track of the number of things in our hash table. So yeah, this is also, sorry, this is also known as a chained hash table, right? So everything that goes into a single bucket, we think of those as being chained together. And then a hash function takes an object and returns an int somewhere in the range of 0 to t.length minus 1. Here I've indicated it by n, but that's, I mean, I'm sort of, that's probably not a great idea. Should be t.length minus 1. So yeah, so we have a hash function, and I want to be able to specify the range of the hash function as well. All right, so everything that hashes to value I is stored in the list at ti. So I just look at the table. If it's all the things that hash to 2 are stored in the list at location 2. All right, so to ensure that the lists don't get too long, as we talked about, we have to make sure that the length, if it's at least n, then on average, each list will have less than 1 element in it, as long as my hash function is sufficiently random. Okay. All right, add is fairly simple, right? This is a unsorted set, which means that if X already exists, I don't want to add it. But find is, of course, I just simply hash X and check that location, and I search through the list at that location. And why did I do add first? I guess I skipped find. That I think that's a bit of an oversight. Right. Well, let's talk about what find would do. Of course, I wanted to find X. Well, I'm going to hash it, of course. So my index I is equal to hash X. And then I will say if t at I dot contains X, return t dot I, or t at I. Otherwise, we return null. Right, so for my unsorted set, the find function is defined as I either return the thing that I found, or I return null if I didn't find it. Okay, so that's my find function. Fairly simple. This contains is, of course, implemented by the, if you use the abstract list interface, it has a contains function. It doesn't always run quickly, but yes, we can, whatever type of list we're using, maybe we have a better function if we wrote it ourselves, but contains, this will work. Okay, so that's the find. If I have a find, then I can do add. If I cannot find the thing, I return false. If adding something to my hash table means that I have too many elements for the size, then I'm going to resize it. Otherwise, I grab the list at hash X, I add the element X, I increment n and return true. Okay, so simple enough. Add X runs in constant time on a list, right? It just adds to the back. Hash X, we're assuming runs in constant time. Now we're going to show you how to do it later, but so nothing in here takes more than constant time. If I call resize, I use the same amortized analysis from array stack. Okay. So yeah, so let's add, as long as I have a good hash function, pretty simple. Questions? Remove is slightly more complex for the simple reason that, well, I do have to search through here. I'm going to have to make some kind of loop, right? So if I call remove X and X hashes to location 2, then I have to search through this list. And I'm going to do it, since it's just a list, I'm going to do it one at a time. I'm relying on the fact that I have a good hash function, that this will be a short list. So I'm just going to do a linear search. And if I find the thing, then I'm going to remove it. And of course, it's going to cost a little bit, but if I'm only storing, on average 3 items per list, it's not going to be too bad. Right, so we didn't really talk too much about iterators, but if I have an iterator, then as I go through the list, I can do a safe remove, right? If you do a for each loop and you try to remove from that list as you're looping, I think you get undefined behavior, but probably you'll get an exception. Exceptions are better than undefined behavior, because undefined behavior, it could be wrong and you don't know it. But yeah, so if you want to safely remove, you use an iterator, and then you can call remove on the iterator. It just walks through the list and then does a proper remove and updates the iterator. All right, so the runtime of remove is, well, hashing as fast. It's basically how much time I spend looking through my list, right? So it's big O of the size of this list. So yeah, add is fast because I can add at the back. Remove, I have to walk through the list potentially. Okay. Sorry, my thing just crashed. Okay, all right. And yeah, so the last thing, I think we'll cut it after this, but find the same thing, right? I just hash into my table. That returns a list, and then I search through the list. Since I'm only finding it, I'm not removing it. I don't need an iterator to safely search. But I do have to, again, I'm going to do a linear search, right? A for each loop. And if I find the thing, I return that thing. Otherwise, I return null. So there is the list. Sorry, there's the find. Okay. So yeah, the find is also, add is O of 1, but remove is O of the size of these lists, and find is O of the size of these lists. So again, the performance of the chained hash table depends on how good our hash function is and how many things we expect on average to find in these lists. So I guess we will continue this lecture. I will update you and let you know if there's going to be a lecture after the midterm. Probably not. But maybe we'll finish this stuff depending on, because I do, there is a certain, if I want to have 5 assignments, I have to get through a certain amount of material. So, but we'll stop here today, and then I will let you know if there's going to be a lecture after the midterm. I will let you know tomorrow. Otherwise, I will see you guys next week for the midterm. Yeah. You guys have the practice midterm. I may update it. If I do, I will let you know. Otherwise, I have office hours on Thursday at 10, or you can drop by basically anytime for 5 minutes, right? As long as you limit it to 5 minutes, I don't mind. And yeah, get your assignment 2 in by Sunday, and of course study, and I'll see you next week.